All right, let's finish out the non-dimensionalization. So we started off with our conservation of a momentum equation. And so for each of those asterisk things, we want to sub in what we found in the last video. So U star was our U times our units V. T star was L over V times T. And this U star with VU shows up in multiple places, here, and over here as well. And then when our grade, we got the gradient still in there. I'm just looking at the left-hand side right now. So let's just focus on the left-hand side. I don't know if I can cover that up very well. Let's do this. There we go. Just looking at the left-hand side. So we've done all our U's, we've done T, we need the gradient. Gradient was 1 over L, we put that in. And so this is this is just replacing that stuff right there. When we factor out or pull out anything that's a capital letter, we can end up pulling out a V squared over L on each of these terms. Okay. We move, this is L over V in the denominator, which when multiplied by the reciprocal, it's going to put the V on top. So we got V squared over L here. We got V times V on top with an E on L on bottom, V squared over L there. So we've got rho V squared over L times that original equation without asterisks. So that's the idea of factoring out the dimensions. And it makes sense. All dimensions on the same side, everything should have the same dimensions. Okay. Let's take a look at the right-hand side. Let's go like this. So the right-hand side, we have the negative gradient of the pressure. So gradient was 1 over L times the gradient. Pressure, we're going to go with the fast flow, the rho V squared version, times the pressure. That will be the units there. And then we've got mu, or just dynamic viscosity, times the Laplacian of U. Mu and U sound so similar. Mu is just mu. We've got 1 over L squared going with the gradient. And then we're replacing our U with VU again. And finally, we had rho G, and we're just replacing G with big G times G. So we want to clean this up a little bit. What do we got going on here? This one clearly has a rho V squared over L, which is good. That matches this. Here we've got UVL squared when we pull out all the things times the Laplacian of U. And this hasn't changed much. And so if I want to address this rho V squared over here and factor it out right here, I need to do a little bit of mojo here. So I am going to, for my UV over L squared, I'm going to multiply it by rho VL over rho VL. So this is really like rho VL here, and I just moved it onto the inside. Rho VL over rho VL is 1. I haven't changed anything, but now I can treat this as mu times rho V squared over L on the inside. And so this is what I want to be able to pull out the rho V squared L, right? So that's what I've done here. And I've still got this part right here, which I'm not showing. I should put right there. Rho VL. So I pulled my rho V squared out L, and I've got mu over rho VL left. I do the same thing with rho G. I'm going to multiply it by, notice if I multiply these two together, it clears out. I've got just rho G again. But here now I've got rho V squared L all together. And I'm left with G times L over V squared. I did write it there. So that's there, and this got pulled out back outside. So now I've got rho v squared L out in front in both places. Okay, so I can divide through them and get rid of them. That gets rid of them. So once we've taken out rho v squared L on both sides, what we're left with is this. We've got the time derivative of the flow velocity plus u times the gradient of u, or not u dotted with the gradient u, my bad. That's the left-hand side. We've got the negative gradient of the pressure plus mu over rho VL times the Laplacian of u plus GL over V squared times G. And so these two things give us two values that show up in the other equation. You saw these on the NASA thing, and I'll bring them back up in a second. If I write this as upside down, if I flip it over, rho VL over u, mu, this is called the Reynolds number. It is the ratio of inertial forces to viscous forces. So rho VL is our inertial forces. Mu was dynamic viscosity. So we can see how that's a ratio. And then B is the Freud number. I think I'm Freud. And they generally, Freud is V over the square root of GL. So we end up getting Freud squared when we put it back in. It's the ratio of the flow inertia to the external gravity field. And so when we rewrite it, we get that. This is what this equation looks like with that. Now that they've got this, they can plug this in the system. And what they do is they fix one of these and vary the other and see how it changes stuff. So if we've got Reynolds at 10,000, what happens is Freud goes from 1 to 10 billion. And they're not doing them in increments of 1. They're doing magnitudes of 10 steps, big steps. So they'll do different magnitudes of 10, 1, 10, 100, 1,000, up to see how that affects for a specific Reynolds number and things like that. This is what they do in big game physics. This was part of my graduate work. The math, applied math teachers at Santa Cruz were working on stuff like this. Just looking at how all this stuff plays out. We'll talk about this more in class. Peace. Oh, that's not what I wanted to go back and show you. The Navier-Stokes. So they show just the 1 over the Reynolds number. You can see the Reynolds number here. They did not show the Freud number here. I don't know that they have external forces in this. I think they're just looking at a 3-dimensional body without external forces. And Freud showed up in the external forces section. So where G was. So that's it. Peace.